multiplying x1 and x2 by some factor, or dividing x1 and x2 by some factor, then I'm moving along a line that has a slope that you can achieve by connecting x1, x2 to the origin. Okay? So think back to additive increase, decrease. Yeah? Do you necessarily have to affect both equally? In practice, yes, because think about how would we decide how much you get to increase, which hosts get to increase by different amounts. That would be a slippery slope to go down. It probably wouldn't be fair. And certainly in this idealized model, we're assuming that. Okay, so in this case, we're moving along a line that has a slope of x2 over x1. Okay, that was just reminders on slopes. So we're going to take these 4 different algorithms and see how they fare in terms of efficiency and fairness. Okay, so our simple model, let's start with AIAD. So that's additive increase, additive decrease. Let's start with a very simple example. We're going to say we're going to increase by 1, decrease by 2. If we had a simple example where we start with x1 equal to 1 and x2 equal to 3, and let's say that the capacity of the link was 5. Right, so in the first iteration, there's no congestion, right? Because 1 plus 3 is 4, less than 5. I'm not congested. So both of them are going to increase. So we now go to 2 and 4. Right? At this point, we are congested. Right? So in the second iteration, we're going to decrease. Each of them is going to decrease by 2. So x1 is now 0, x2 is 2. We're underutilized. So in the next iteration, there's no congestion. We're going to increase. So we're going to have x1 equal to 1, x2 is equal to 3. Right? Everyone's good with this? Yeah? The thing to notice is we've not improved fairness at all. The gap we had between x1 and x2 has stayed the same throughout. From an efficiency perspective, you could say we're doing the right thing, right? You're never going to land exactly at the efficiency point. So sometimes you're going over, then you're going under, then you're going over, then you're going under. You're oscillating around full capacity, and that's fine. But you're oscillating around without improving fairness at all, and that's not okay. Right? What that looks like in our graph here is that if you started with x1, x2, and you're doing AIAD, when you decrease, you move down along a line that has a slope of 1. When you increase, you're going back up along the same line with a slope of 1. So you're never moving your operating point towards the fairness line. Okay? Does that make sense to everyone? Okay. So it doesn't converge to fairness. If we do the same kind of example with MIMD, and I'm going to do it fairly fast, but stop me if you have any questions. Right? If we said now MIMD, I'm going to increase, let's say in this example, 2x, and I'm going to decrease by dividing by, let's say, 4. And if I start with a rate where x1 is half and x2 is 1, and my capacity is 5, and let's walk through that again. So in the first iteration, no congestion, right? 1.5 is way less than 5. So they're both going to multiplicatively increase. Multiply by 2, you get x1 is 1, x2 is 2. So 1 plus 2 is 3, less than 5, we're still not congested. So in the next iteration, we multiplicatively increase again. So now we get 2 and 4. 2 plus 4 is 6, we are congested, so now we need to drop. Right? So we're back, x1 has half, x2 has 1. And you could continue on. Same as before, we are oscillating around congesting and not congesting, congesting and not congesting, which is good. That's what we want to do for efficiency. But we're not, again, reducing the gap in fairness between x1 and x2. Okay. Make sense? Going back to our picture of why that is, we're just moving along the line that has a slope of x2 over x1. But again, we're never moving that line closer to fairness. Again, doesn't converge to fairness. I want you to do MIAD. Play with it and see what happens. Let's say I'm going to make it easy and give you an example. Take 2 minutes. question.
I was wondering about if it's exponential upward, but not from one that it's exponential when we're
The slow start phase?
very first.
Because when you're bursty, and as you increase the load, and this is actually like an MM1 queue with Poisson arrivals. So the model it has is of an infinite buffer queue. And so your delay just keeps going. Because once you're bursty, you kind of, as you go to high load and you have bursts, you fill the queue and then you never have a chance to drain it when you're at high load. So every burst just keeps adding to the queue. Okay. A control theorist would cringe at that explanation, but yeah. Okay, thoughts? How does MIAD fare? What did you find? Yeah? Less fair, exactly. How unfair? Yeah. So let's walk through an example here. So in the first iteration, we had x1 and x2, 1 and 3. There was no congestion, so they both multiplicatively increased to 8, 6 plus 2. So the second iteration, we have congestion, they'll cut down. Third iteration, cut down again. Fourth iteration, no congestion, go up. Now look at what has happened here. x1 is at 0 and x2 is at 8. Right? And so you could keep working through any of these examples that you take different values, different numbers of steps. Where you will end up is always that one of the flows gets 0 allocation. And so MIAD is actually maximally unfair. And if you look at it in terms of the graph, what you'll see is it moves along a direction that will take you to either the x or the y-axis. So play with it on your own, but what you should always find is that one of the flows gets 0 and the other one gets all the capacity. So MIAD is the worst of all these options. Let's walk through what AIMD does. So let's consider here that you had an increase of 1 and a decrease of 2. And if we started again with the same example, x1 is 1, x2 is 2, you have a capacity of 5. I'm not going to actually step through all of these, but you can do it offline. Calculate the x1s and x2s you end up with each time. What you're going to find if you look at, as you go forward and you look at the difference between x1 and x2, we started out with x1 being half or 1 off from x2. And as you continue to proceed, you're going to see that the difference drops over time. So just like the other schemes, we are oscillating above and below the efficiency line, but now the gap between x1 and x2 is shrinking. They're getting closer to fairness. And so the difference between x1 and x2 decreases. It stays constant when you're increasing, but every time you decrease, the difference halves. And this is very clear when we look at the picture, because what's happening now is when you decrease, you move along that line that had a slope of x2 over x1. But now when you increase, you're increasing along a line that has a slope of 1. Right? So you're shrinking the gap to the fairness line by this angle over here. And as you continue to decrease and increase, what we start seeing is that you're moving x1 and x2 towards that point. Okay? And so AIMD is the only one of these options that we can show converges to fairness. Any questions on this? Okay, great. So the answer to why AIMD, it embodies this sort of gentle increase, rapid decrease philosophy, and it's the only choice that's going to drive us to get both fairness and efficiency. Now, the example that we walk through with this model is it's kind of a toy model in the sense that there are only two flows, they're both reacting in lockstep, but the general intuition holds for why AIMD is the right solution. Okay? So out of the four options, AIAD and MIMD retain unfairness, they don't improve it. MIAD makes it worse, it's maximally unfair, and AIMD achieves both of them. Any questions on that? Okay, so with that, we now have a fairly good sketch of a solution, right? We said that each source is going to independently run this algorithm here, where you pick an initial rate, try sending at that rate, check if you had congestion, and then adjust, right? What we now know, and this is a sketch of TCP's solution, is that the way in which you pick that initial rate is based on slow start. Right? You pick a small value and you exponentially increase it until you see loss. And we also know that the way you decide whether you experience congestion is whether you had loss during that time interval. Okay. And we now know that the way you reduce your rate is you multiplicatively decrease by some factor. In TCP's implementation, that's 2x. And if there's no congestion, you increase your rate additively, right? AIMD. So in TCP, again, that's +1. Yeah? +1 MSS per round trip time, which we'll do when we get to the details of TCP. Any questions on this basic approach? Okay. And so if you play that out, one of the things you'll hear when people talk about TCP and the throughput you expect to see when you get TCP. So a fun way is actually run an experiment, open a TCP connection and look at the throughput you're getting. You should see something that people will say TCP has a sawtooth behavior. And what that tends to mean is that if you look at, over time, what is the rate or throughput that you're getting from your TCP connection, you'll get a graph that looks like this, where the initial phase is the exponential slow start. So you're exponentially increasing your rate until you have a drop, at which point you multiplicatively decrease your rate. So you get this line coming down. And then finally, you increase your rate additively. Okay, so you're linearly increasing your rate until you get another loss event when you cut down again multiplicatively and then increase linearly and drop. So you get what people call a sawtooth looking graph. Any questions? Okay. So with that, next time, details of TCP, congestion control is really pretty much what we've talked about, but we're going to step through it in a fair amount of detail. The few key differences is that TCP doesn't think in terms of rates, it thinks in terms of windows. Right? So are you increasing your window or reducing your window? And it's going to do everything we said that I'm going to try sending at this rate and decide whether I have congestion or not. The time scale for that is going to be a round trip time. Right? So every round trip time, you're going to try and adjust your window, either double it or halve it or increase by 1 and so on. And we're going to get into certain details like TCP has different reactions for loss-based because of timeouts versus duplicate acts. And TCP does reuse slow start, so it's not just at the beginning of a connection, and we'll get into that as well. With that, any questions? No? I think I'm done for the day then. Thank you. Yeah. I didn't get that.